scattering, what we are doing. So what we are doing, so we had a discussion on scattering. Okay, scattering states application problem. Okay. So we considered a potential. Okay, so this is very important. The problem is what we are doing. No. So you are having, so we had this kind of condition. This potential goes to zero as this goes to clear? So it falls off to zero. This was very important condition in our problem. Clear? So let's consider this kind of potential. So let's consider. So let's assume this is the kind of potential that we are looking at. So you are saying this as Vx and this as x. Okay, so this is simply a rough sketch. Okay. So now we will consider the scattering of this kind of. We will be looking at the scattering states instead of the bound states. Okay. So for such kind of potentials, the scattering states are having positive energy and the bound state are having negative energy. Clear? And we represented these scattering states as what? E raised power plus minus I k x. Clear? So we are considering the one-dimensional motion, not the higher dimensional motion. Clear? Okay, so now let's consider the scattering from left. Okay, let's try to understand. Suppose if I throw particles from the left, what will happen? Since we are dealing with the quantum mechanics, so there are the possibilities. So the particle may get reflected back and it will get transmitted. Okay, so classically that is not possible. Okay, classically that's possible only when the energy of the incident particle is larger than the height of this very potential. Clear? But quantum mechanically it is true if the energy is less than this barrier height. Clear? Okay, so what we can have if I am throwing particles from left, so I'll be having, okay, so this I call x equal to minus infinity region. So that means the left side. So let's call this as x equal to plus infinity region, because we are in the asymptotic limit. So in the asymptotic limit, what I mean by that, the particle which I threw at the potential, it does not interfere in this very region with this very potential. It's only in the localized space where it will get affected. Okay, so it is free here. That's why I put it as x equal to minus infinity. It is the asymptotic region here and the asymptotic region here, where particles are essentially free. Okay, so what is the form of the wave? So if I put, so what is, I need to solve the Schrodinger equation. Okay, and the Schrodinger equation will give me the solution for these free particles as exponential of this thing, e raised power plus minus I. So you have it here for first time? आप किसी कहाँ से? आप इसी यूनिवर्सिटी से? So I can have this kind of possibility. So e raised power I kx, it's a wave that's moving towards right, starting from left to right. Okay, so I can be having the possibility. So there is a reflection. So e raised power minus I kx. Okay, because k will change the sign. So this is a wave. So that's moving towards what? Minus x. Towards x equal to minus infinity. Since I am considering the okay, so only one side. So I'll be having this kind of possibility. E raised power I kx. So there is no reflection here. Okay, mathematically saying that the solution, what I am considering, so that part of the solution is 0. Okay, so you can solve a Schrodinger equation either for this region or for this region. Okay, so now let me write. So if I consider now the scattering from left, what I mean by that, so let me write the wave function. Okay, so let's write, let's club these terms. So what is the possibility? I will write my psi r. Psi r means the right moving wave. Okay, because they have started from left to right. So just understand notation. Okay, so this is the possibility what can happen. Okay, I can write now this is the solution of the Schrodinger equation, solving a problem on the left side of this very potential. Clear? Okay, so this can happen. So you will be having e raised for I kx. Okay, plus let me introduce a constant, okay, some variable r, and e raised for minus I kx. So this is the region, asymptotic region x minus infinity. Okay, while r is a complex number in general. So let me tell you in a moment. And there is another, okay, solution. So e raised for I kx. So let me introduce here t. So t is not time here. Okay, so this t is not time. So it is in the region x plus infinity. So these are the asymptotic solutions for this very problem. Clear? So this r and t, they are complex numbers. Okay. So we call this as the reflection amplitude. Okay, so this we call as the scatter. Okay, transmission amplitude, or the amplitude for the transmission. Clear? Got it? On this side, what? So you are having in this region these two waves, but it's not necessary. Why? Okay, I have normalized it such that the coefficient here is 1. So because let me throw a particle, okay, on the potential, so it may get reflected with certain probability or it may get transmitted with certain probability. That's why I introduced these kind of coefficients. Okay, got it? Okay, good. So what is the probability? Okay, so reflection probability. So let me write that as r. So it is mod of r square. It is the probability for reflection of the barrier. And let me write the transmission. So it is mod of t square. So it is the probability for transmission. Okay. So before going, let's having the explicit calculation. So let's analyze a few things of this kind of psi r. So then we'll take if we are throwing, let's say, particles from this side. Okay. So we'll then go on this side. First, let's analyze certain properties of this R and P. Everybody followed it? Okay. So, so this is actually the convenient way if you have to solve a potential problem, because we will generalize it to more complicated cases. Okay, so this will be very useful. But I will not use this kind of thing. So we'll complicate it. I mean, so for more complicated problems. So okay, so let me put it this way. What I am trying to do, we'll look at simple scattering problems. Clear? Okay. So then generalize it. Okay. So then try to figure out a quantity or a matrix, what we call the scattering matrix of a given problem. Okay. From scattering matrix, you can calculate scattering states as well as the bound states. Okay, you can look at the bound states of the problems from the scattering matrix as well. Scattering matrix is the crux of the scattering theory. If you know the scattering matrix, you know everything. Okay, so we are going actually in that direction to figure out the scattering matrix. Clear? Okay, so why it is, although I am developing the formalism for the scattering states, but ultimately we will reach out to the bound states from these scattering states as well. Okay, so think of a deuteron problem. So you are having a weakly bound state, clear? Or where you can be having a weakly bound state, or the bound states which appear because of the scattering. So let's say you are having a particle within the two delta functions. Okay, so that's trapped within the two delta functions, and the particle gets scattered of that delta function. It is possible you can be having a trapping of the particle. Clear? So when the particle gets trapped by the potential, it is a bound state. Okay, so but we can calculate that kind of thing from the scattering matrix. Okay, we will see it. We'll look at the resonances in the scattering from the scattering matrix, and that's the formalism I'm trying to develop for that scattering matrix. Clear? So we'll do it from this way, then we'll do a general theory kind of thing. Okay, for the timing we will use simple these arguments. Okay, so now let's look at Okay, so let's calculate the current. So if I know, let's say, so if you are having some psi of x as solution to Schrodinger equation, so I can calculate the conserved probability current. So this psi satisfies what? So you are having, you know, so you are having the conservation rule of the probability del dot j equal to 0. So what is j? J is the probability current. So you consider the surface across which this current flows. Okay, and within that surface, that is the volume where the probability is changing. Clear? Okay. So you write this j as minus I cross by 2m. Okay, psi star d psi. So we are in one dimension. That is why I will put d by dx. Okay, then you are having this psi. Okay, d psi star by dx. Clear? Got it? So this is the okay. So what you are having? So this equation means you are having. So this probability is conserved. dj by dx is equal to 0. So this is a conservation law for this. So this is a conserved quantity. In other words, this is you can put this current in terms of the Wronskian. So you can put the Wronskian of this. So let's assume you are having the two solutions of the Schrodinger equation, psi and psi star. So then you can construct the Wronskian psi star, let's say psi, then d psi star by dx. Okay, d psi by dx. So this is the Wronskian. So mathematically saying the conservation of this j implies the Wronskian is what? What is Wronskian? Huh? Tell me. Wronskian vanishes. So there are two linearly independent solutions. Psi and psi star are two linearly independent solutions of this very problem. So that's what I mean by the Wronskian goes to 0. Clear? Or we can say Wronskian is actually constant, because j you can put in terms of this w. Okay, dj by dx is equal to 0. In other words, w is constant. Clear? So if this Wronskian is constant, you can say these are two linearly independent solutions. Okay. Okay. So now let's calculate the j for this psi r. Okay. So let's calculate. So therefore, for psi r, I can have this j. Okay. So now let's look at this this asymptotic region. Okay. So you are having this x minus infinity in this region. So let me write it as j of x. Okay. So what is that equal to? Okay. So what is the solution? Psi and psi star. Let's put psi star. Okay. So you are having minus I cross by 2m. Okay. What is psi star? E raised power minus I kx plus r star e raised power I kx. Clear? Then you are having the derivative. So now let's differentiate that solution d psi by dx. So I k will come down. Clear? So you are having I k. Then you are having e raised power I kx. Okay, so here it will be minus because you are having minus I k here. Clear? So you are having minus. So it is r e raised power minus I k x. Then you are having actually the conjugate term. So minus, let's write psi. It's e raised power I kx plus r e raised power minus I kx. Then the differentiation of the star. So it is minus I k will come down. Okay, then you are having e raised power minus I kx. Then minus r star e raised power I kx. Clear? Got it? So now I and minus I, it will become plus. Clear? So this minus and minus become plus. So k, you are having h cross something. Okay, so you just simplify it. So j of x, it will be simply h cross k by m. Okay, into 1 minus magnitude of r square. Okay, now look here. So you are having this e raised for this thing, and then you are having r star and r. So it is mod of r square. Okay, so it's 1 minus r square. Similarly, you are having e raised for this thing. So it is 1 and r star, it's minus mod of r square. Okay, so the cross terms will cancel out. Got it? So this is your current. So it is in which region? The left of the potential. Clear? Okay, so now let's calculate for the right side. So you are having, okay, for this x tends to plus infinity region. So what is your J? Now let's calculate J for this region. So it's minus I star by 2m. Psi star, it is simply T star e raised power minus I kx. Now d psi by dx, so it is T, okay, I k e raised power I kx. Then minus, okay, psi, it is T e raised power I kx. Then the differentiation, so it is T star minus I k e raised power minus I kx. So how much is that? So it's simply h cross k by m magnitude of t square. Okay, t. Clear? Got it? Everybody followed it? Okay, now if you are having conservation of the probability current for a given problem, what does it mean? So the current on the left has to be same as current on the right. Clear? So let's equate the two. So let's equate the two. So on equating, so equating two expressions, what does it mean? So it means h cross k by 2m, okay, 1 minus magnitude of r square, that is h cross k by, sorry, m, okay, magnitude of t square. What does it mean? So 1 minus magnitude of r square is same as this t square. What it gives me? Magnitude of this r square plus magnitude of t square is equal to, what is r magnitude of r square? It is the reflection probability plus transmission probability is equal to unity. So this is simply the conservation of the current or conservation of the probability. Got it? So now you have got the relation between the two things. Huh? So this is very important identity. Huh? Okay. So now let's look at the scattering. If we consider scattering from right of the problem. Clear? Okay. So let me consider it from right. So what does it mean? Suppose you are having this potential. Let's say this is our potential. Clear? So I am considering now you are throwing particles from right. Clear? So what is the right moving wave? Rather the wave that comes from right to left. So this is x equal to plus infinity. This is x equal to minus infinity. What is the wave? So you are having e raised power minus I kx, and there will be actually the reflection. So it is simply e raised power I kx. So what it will be here? So e raised power minus I kx. So it has come from right to left. So let me write now our asymptotic wave function. So psi left I will put as, now tell me, what should I write? So I will write e raised power minus I kx plus, let me introduce r prime to be the reflection coefficient. Clear? Because I am considering now that, okay, so I started from left, now I consider from right. Clear? So instead of writing r, I will put as r prime. Okay? So this analysis will be actually useful when the potentials are not symmetric. When the potential on the, okay, two sides it is different, so it can be entirely different. Okay, it cannot be the symmetric potential. That's why it will be very useful. Okay, so since I am considering an arbitrary potential which vanishes in the asymptotic limit, so this holds. Okay, so what it will be? E raised power I kx. So you are having the domain, this domain. Now I will introduce the transmission coefficient t prime. So e raised power minus I kx. So it's x tends to minus infinity. So this is the asymptotic wave function or the asymptotic solution for if you consider the scattering from the right. Okay, so now let's ask the question. is there in a relation between the psi r and psi l? Okay, is psi r, that means the right moving wave, related to the left moving wave, or does there exist any relation? Or in other words, are these the coefficients of the reflection and the coefficient of the transmission are the same if you consider the scattering from left or scattering from right? Okay, clear? Yes. Okay, so let's try to understand that. Let's try to understand that kind of relation. Okay, so since okay, so this potential what we have considered in the during this lecture, it's a real potential. I am not considering any complex potential. Okay, so if I am having a real potential, what does it mean? So let's look at the Schrodinger equation. So you are having this Schrodinger equation. Okay, so if you can, let's say, okay, if this Vx is real, got it? It means if psi is a solution, implies psi star is also a solution. Okay, so the complex conjugate is also a solution. You can complex conjugate this very equation. Since V is real, okay, then, okay, so if you complex conjugate psi star, it will be V star psi star E psi star, clear? Now V is real, so that means psi star satisfies this differential equation. It is a solution. So by linearity, since I am having linearity of the solution, it means psi plus, let's say, A psi plus B psi star is also a solution. Got it? Okay. So now let's look at this psi r. Okay. So I am having this psi r is a solution of Schrodinger equation. Clear? So what does it mean? Psi star r is also a solution. So it means I can take now the linear combination. Okay. So let me take this kind of linear combination. Psi star minus r star psi r is also a solution. This is by linearity. Yeah? Clear? Got it? Okay. So let's calculate this psi star on this very object. Okay. So you are having this psi star r minus r star psi r. So let's calculate this. Yeah? What was our psi r? Let's look at x equal to minus infinity region. Okay. So what is our psi r? Okay. So let me write psi r for you people here. E raised for I kx plus r e raised for minus I kx, so x tends to minus infinity, x t raised for I kx, x tends to plus. Now let's take this very quantity. So I am having psi star r, what that will be? E raised for minus I kx plus r star e raised for I k x, got it? Okay, minus r star. Okay, then you are having psi r, so it's e raised for I kx plus r e raised for minus I kx. So what is the region? Left region. Okay, then you are having this psi, so it is t star e raised for minus I kx. Then you are having r star psi r, it is t e raised for I kx. Okay, x tends to plus infinity. That बात मतलब okay. So what is that equal to? Now let's calculate. So you are having e raised for minus I kx. If there is some error probably. Okay. So now let's look at this very thing. So you are having this term and this term. They cancel that. Okay. So you are having here e raised for minus I kx plus minus magnitude of this r square. Clear? So r square e raised for minus I kx So, yes. No, it should. It should not be mod of R square. So let me check. So I have made an error somewhere. Huh? Have I made an error? Yes, it's okay. It's okay. It's okay. So it is x tends to minus infinity. So now what I am having here? So it is something t star. Okay. E raised power minus I kx minus I star t. Okay, so let me take this t star out. So I will divide by this by t star e raised power I kx. So that's x equal to plus infinity. Got it? Okay. So, Hilal? Huh?
It is or magnitude of or square.
Yes. Okay. Wait. No, wait. So you are having e raised power minus I kx. Okay. So this term and this term cancels. Clear? Minus magnitude of r square e raised power minus I kx. Clear? Because it is which term? This term, huh? Okay, it is psi r star multiplied by psi r. Got it? Everybody?
Yes, sir.
Okay, good. So then you are having t star. So psi star is this thing. T star e raised power minus I kx minus r star psi r, that's t e raised power I kx. Got it? Okay, so you are having now this very object and this thing. So here I have taken t star out. Huh? So divide by, so r star t and t star. Clear? Everybody followed it?
Yes.
Okay, good. So this is very important thing. So you should. Yes. So what you are having now? So you are having this psi star L minus R. Sorry, psi star R minus R psi R. So this is actually equal to 1. Okay. So now look here. So this is actually equal to. Okay. So 1 minus magnitude of R square into e raised power minus I kx. Clear? So this I can write as, so magnitude of t square e raised power minus I kx. Clear? So in other words, this is simply t star t e raised power minus I kx. Got it? Okay. So this I can write simply t star t e raised power minus I kx. So what is the asymptotic region? Minus infinity. So here you are having this t star, okay, e raised power minus I kx minus r star t by t star e raised power I kx, x tends to plus infinity. Okay. Now if you see in both the terms, this t star is multiplying, is it? So you are having t star here, t star here. What I can do, if I normalize my these waves, clear? So to have, okay, in order to compare this very object with that psi L, so I can have, okay, I can agree upon some normalization constant, clear? So I can divide throughout this equation by this t star, clear? What remains there? Okay, so if I divide this equation throughout by what? T star, so it will remain t e raised power minus kx and this object, okay? Got it? Okay, so if you divide throughout by this t star to agree upon some normalization, certain normalization, then you can have this variable. Clear? Got it? So I have not written that, so I have just removed t star. Got it? Okay, good. So now let's look at the two equations. Since this is a solution in which region? Right side. Clear? Got it? So that is, this is a valid solution and that's a left solution. Now look here, what is the relation between the two? So look here, you are having asymptotic domain x equal to minus infinity, is it? So what is there? X equal to minus infinity. What that means? T prime is same as t. So let's call this as equation. Let's assume this 2. So this was 1. So let's call this as 3. So from second and third, we get, okay, the relation. So t prime is same as t. So that means transmission coefficient is same whether you consider scattering from left or scattering from right. So the transmission coefficient will not change. Okay, so what about now this thing? So you are having e raised to minus I kx there. It's r prime, so r prime is related to r by this very equation. So if you see, this is simply actually, so only the reflection coefficient gets a phase change. This is simply a phase change. If you see what you are having t here and t star here. If you divide these two, t and t star, you will get a phase change. Yeah. So let's put t as a complex number. T is equal to some t0 e raised power I phi, and t star will be, okay, so if I write t is equal to some t0, it's a magnitude, some kind of thing, e raised power I phi, just the complex representation. What will be t star? So it is simply t0 e raised power minus I phi. Now let's divide the two, t by t star, so that will be e raised power 2I phi. So that means reflection coefficient suffers a phase change. Got it? It's very important. So that, okay, so if you consider any arbitrary potential, whether you consider reflection, okay, whether you consider the scattering from left or right, transmission coefficient will not change. Only there will be change in phase of the reflection coefficient if you consider reflection from left or reflection from right. But if you take the magnitude of the two, okay, so that means t, okay, so let's take the magnitude of the two things, magnitude from square, okay, so the transmission probability is same and also the reflection probability is same. Is that true? So if you take magnitude of this thing square, so it will be same as magnitude of r square. So that means probabilities will be remain same. Only the phase change will occur in the amplitudes. Got it? Okay. So now let's look at an example. Okay, so this result I require. So this is a result I will put here. So I require this result. Okay, so this I require. So let's consider. Okay. So we'll consider a potential. Some potentials. So what we some potential there, huh? Finite potential. Okay. So this is the potential there. So let me consider. So let's have, okay, so this is, so the depth is V naught, so it means this is minus V naught. Okay, magnitude, okay, so depth of this well is V naught. So this can go to the infinity as well, you can tune it. So but we'll consider the finite, that means the depth of this thing is finite. Okay, so it's minus a by 2 and this is, let's say, plus a by 2. Okay, so this is 0. So the 0 is like this. So this is the origin. So this is x-axis and this is your potential. Clear? So this is the origin here. Okay, so I will not draw this line. So you should. So it is not actually separating the value. So just it is, these are simply the axes. Okay, so what is our potential we are looking at? We will be solving this for the scattering states. So this is equal to minus V naught for x belonging to minus a by 2 plus a by 2. Clear? And it is 0 otherwise. So let's consider the scattering. Let's solve the Schrodinger equation for the scattering states. Got it? What does that mean? What we need to figure out? So we need to calculate simply the reflection probability and the transmission probability. Okay. So let's consider now the scattering from left. Got it? Okay. So there are certain things to remember. First is wave function is continuous always, and the first derivative of the wave function is continuous only when the potential has a finite discontinuity. If the potential does not have, if the potential suffers a singularity, then the first derivative of wave function is not continuous. It is discontinuous. Got it? Okay, since you are having a finite discontinuity in the potential, so the first derivative is continuous. So remember it. So these are the two things we require. Okay. So if I consider now my scattering from left, okay, so let me write your having psi r is defined now. Okay, so I need to match, okay, for this very problem, the wave function at this minus a by 2 and wave function at plus a by 2. For that matter, I need to figure out what is the wave function that exists within the box. So in the these asymptotic domains, I know what is the wave function. If I am considering the, let's say, scattering from right, so my wave function is psi r. It contains both the incoming, outgoing waves. Now I need to figure out what is the wave here. Okay. So for that matter, so you can write, okay, so you are having this Schrodinger equation, d2 psi by dx2 plus v, okay, v psi, okay, v of x psi is equal to e psi. So what you get? So you are getting this kind of differential equation. So minus 2m by h cross square. So e minus v of x psi. Clear? So you can write it as simply minus q square psi. Got it? What is q square? So your q square is equal to 2m by h cross square. So e minus v of x. So for our case, it is 2m by h cross square e. Okay, this v of x is minus v naught. Okay, so it is twice m v naught by h cross square. So this is simply k square plus twice m v naught by h cross. What is our k square? So it is twice m e by h cross square. Got it? So remember, our q square is what? It's this very objective for our potential. What we are considering, it is k square plus this thing. So this is a very important quantity. Now you are having a second order differential equation. Okay, so within that region you can put now the solution. Okay, psi of x equal to, let's say, e raised power a, okay, I q x plus b e raised power minus I q x. Got it? Samajh? Because, okay, so you can figure out the solution. So you can substitute it here. So you'll get it as a solution. Got it? For second order differential equation, you require two constants. So you are having a and b here. Got it? Okay, so I will write therefore. Okay. So within the valve, okay. So my wave function is psi of x equal to a e raised power I q x plus b e raised power minus I q x. Okay. So here x belongs to minus a by 2. Okay, and this q square is equal to twice m v naught by h cross square plus q square. Okay. Okay, so now let's apply the continuity. Okay, so first case is, so let's look at x equal to minus a by 2. Got it? So wave function is continuous. So I'll do it in detail. So continuity of psi. So what is wave function at x equal to minus? Okay, so this wave function. What is that? This one. Clear? Is that true? Okay. So you are having e raised power I k a by 2 plus r e raised power minus I k. Sorry, minus, it is plus because it is x equal to minus a. Huh? Okay, so that's equal to now a times. So what is the wave function inside the valve? So this thing. So a e raised power minus I q a by 2 plus b e raised power I q a by 2. Everybody followed it? What I heard? Huh? Everybody? Okay. So now what about, okay, so let's call this as 1. So what about at x equal to plus a by 2? So let's look at x equal to plus a by 2. So what is the wave function at x equal to plus a by 2 in the asymptotic region? It is this thing. Clear? So you are having then t e raised power, okay, I k, no, not minus. It is plus a by 2 because asymptote it is t e raised power I k x here, is it? So that means I need to look at the continuity at this very point. Sumation? Okay. So that's equal to a e raised power I q a by 2 plus b e raised power minus I q a by 2. Let's call this as second. Got it? Huh? Okay. So now let's look at, okay, so second point is, let's look at the derivative d psi by dx. Okay, so at first point is, so I should have put it here. So this is at x equal to minus a by 2. Okay, clear? So this way. So this is here. So let's write at x equal to minus a by. So now tell me, at x equal to a by minus a by 2, I need to put the derivative. Okay, so let's differentiate this thing. Huh? Okay, so let's differentiate. What I will get? So I will get I k e raised power I. So it will be minus. Then you have to substitute for x minus a by 2. Clear? Okay. So then minus I k r e raised power. So it will be simply I k a by 2. So that's equal to a. This thing. So differentiate it. I q will come down. Okay. So it will be I q a e raised power minus I q a by 2. Then minus I q will come down, minus I q b e raised power I q a by 2. Clear? So here x equal to, you are putting x equal to minus a by 2. That's minus, this term minus, and it is plus here. Clear? Okay. So now let's rewrite it in a good fashion. So what you are having? So I and I you can cancel throughout. So I'll be having this simply k by q, like this thing, e raised power minus I k a by 2 minus r e raised power a by 2. That's equal to, okay, a e raised power minus I q a by 2 minus b e raised power I q a by 2. Let's call this as third. Similarly, you can be having, okay, so now the continuity of d psi by dx at x equal to plus a by 2. Clear? So let's calculate that. So at x equal to plus a by 2. So let's calculate the derivative. Just tell me. So I will keep it for the time being. What is the derivative of this? It's I k t. Okay. So you are having I k t e raised to I k a by 2. So what is the wave function inside? That is this thing. So it is I q a e raised to I q a by 2 plus, sorry, it is minus I q b e raised power minus I q a by 2. Clear? So what you are having, so it means, so let's write k by q, okay, t e raised power I k a by 2, it is equal to a e raised power I k a by 2 minus b a by 2. So this is equation 4. Got it? Everybody followed it? Yes. Okay, so now you are having 4 equations in 4 unknowns. A, B is unknown, R and T is unknown. Because for this problem, we don't know what is R and T. So 4 equations, 4 unknowns, that means it is an exactly solvable set of equations. What I will do, I will eliminate A and B first. Okay? So let's take first and third equation and eliminate A and B. Clear? So let's add and sub. Okay, so let's add first and third. So this term will cancel. Clear? I will get an equation for A. And similarly, I will add second and fourth. So I will eliminate B. So I will get 2 two equations for A. Okay, so let's write it. So eliminate first A and B. So let's add. Okay, add first and third. Okay, so let me write it this way. And you add here. Add a third. Sorry, second and fourth. Clear? Okay, so now let's add this first and third. What I will get? I will get A e raised for this thing. You sure?
Yes, sir.
So coefficients of A is same. So it is A. It is twice A e raised power minus I q A by 2. So that's equal to. Now tell me what you are having on this side. So the coefficients here, e raised power minus k, e raised power minus k, it will be simply 1 plus k by q, e raised power minus I k a by 2. Huh? Clear? Then you are having plus r is same. Clear?
Minus I.
So what you are having? Just tell me. So it is r into 1 minus k by q e raised power I k a by 2. Got it? समझ आओ?
Yes.
Okay. So you can divide this. Okay. So r, what is a? So it is 1 plus k by q. Okay. So it is half e raised power. Okay. So it will go on this side. So what you will get? E raised power. When you? So it is minus I k is here. When it goes down, so it will come. It will be plus. Huh? So it is something I k minus q a by 2. Okay, so it's plus q, huh? Plus half r into 1 minus k by q. So e raised power I k plus q a by 2. Got it? So this is A. So now let's add second and fourth. I will do only this set of equations. Okay, so rest you will do yourself. Let's take second and fourth. So this is second and fourth. I will get again A. A e raised power I q. So it is twice. Twice A e raised power I a by 2. So that's equal to t plus. Okay. So like this thing, t will, you take it common. So it's 1 plus k by q e raised power I k a by 2. So what you will get? So what is A? So it is half a t into 1 plus k by q e raised power I k minus. Okay, so k minus q a by 2. Got it? समझ आओ? So now you are having value of A here, value of A here. So both must be same. Got it? So in other words, okay. So this is from addition. Now if you do the subtraction, you will get for B. Clear? Okay, so you will eliminate B. I am eliminating A here. Eh? So I'll write those things directly. So which implies therefore from these two things, I'm having half and half will go. So I'll have P into 1 plus K Q e raised power I K minus Q A by 2. That's equal to 1 plus, okay, e raised power minus I K minus Q A by 2 plus R into 1 minus K by Q into e raised power I K plus Q A by 2. So let's call this as fifth equation. Similarly, eliminating B by subtracting. By subtraction, what you will get? Okay. So can I write that result directly? So we'll get this kind of equation. Okay, so here you can figure out T. Clear? So Samashma, just figure. Okay, so let me write this T is equal to. So you can divide it here. Huh? Got it? Okay, so you can divide this object on this thing. So you will get some T from here in terms of R. Clear? Okay, so let's call the. Okay, so let me first write this eliminating B. So you'll get T into 1 minus K Q by 2 e raised power I K plus Q T by 2. That's equal to 1 minus A by 2 plus R into 1 plus K by Q e raised A by 2. Let's call this equation 6. So now look here, look at the equations carefully. So you are having this now equation in T and R. This is equation in T and R. Clear? You can eliminate T, you can eliminate R to figure out one of the variables. Okay. So let's calculate T. Okay. So now look here. Here you can calculate. Okay. So I will tell you. So you can calculate T from this equation. Something that's in terms of R. You can calculate from this equation T. Clear? So equate the two then, because you have got the same values for T. So what you will get ultimately? An equation for R. Got it? So if you write that, so I'll do it there quickly. So you will get T is equal in the first, okay, from fifth. So you will get T is equal to e raised power minus I, a minus q a, because 1 plus q, this factor is same on the both terms, that will cancel, and in the other case it you divide it. So it is r into q minus q divided by q plus q, e raised power I q a. Okay, and from that's equation 6, t is equal to e raised power minus I k plus q a plus r into q plus k divided by e raised power minus I q a. Call this as 7, call this as 8. Now they are same. Okay, so they are the same things. So it means, okay, so which implies 7 is equal to 8. Got it? Because you are having the values up. So what will be r now? Okay, so let me write. So which implies e raised power minus I. So I will calculate only this r. So plus r into q minus k divided by q plus k I q a. So that's equal to minus I k plus q a plus r q plus k divided by q minus k. Okay, so take this term on this side. So what you will get? So e raised power minus I k minus q. Okay, a minus e raised power minus I k plus q a. So that's equal to, take r on. So it is r into, so that term minus this term. So it is q plus k divided by q minus k my, okay, so e raised power I q a minus q minus k divided by q plus k e raised power I minus I q. Sorry, so this is minus and this is plus, like this. So now rearrange the factors. Now look here, e raised power minus I k a, it is same in both the terms. So you take it out. Okay. So it's simple. So take that. So you are having e raised power minus I k a, take out. What remains inside? E raised power plus I q a minus e raised power minus I q a. That's twice I sine a q a. Clear? Got it? Then that's equal to r. So what remains here? So just multiply the two. So q plus k, this thing, it will be square. This into this thing will be square, divided by q square minus q square. Got it? So I'll write it in the denominator. What you are having? Q square minus this thing. So you are having, okay, so let's write. So you are having q square plus this, do it, right? So can you do it? Okay, so it will be like this thing, q square plus k square, okay, into minus twice I sine of qa. Okay, now look here how it's e raised power minus I qa minus e raised power I qa. That is minus twice I sine of qa. Just rearrange the terms. Okay, plus twice qk. Okay, so multiplied by twice cosine of qa. Okay, so now what you calculated? R. So R is equal to simply, okay, so you are having twice I here minus twice I here. So I will take this minus twice out. So put it as minus q square and plus q square. Got it? So I will write it like this thing, k square minus q square. So it will go on this side. So it is sine of QA e raised to power minus IKA divided by this objective Q square plus K square into sine of QA plus twice QK, okay, cosine of QA. Okay, so similarly you can calculate now T. Okay, so this will be home assignment. So what you have to do from the equations, so the subtracted equation what you have done from there are the T equations I have calculated. Here you from 7 and 8, okay, you have calculated T, so you instead put it in terms of R, okay, and eliminate R, you will get T. Got it? So that is simply equal to, okay, twice. Okay, now look here, the problem is so simple, but these coefficients are very complicated, huh? So you are having Q square, so we need to interpret these results, huh? What exactly it means. So since you are having T is non-zero, so it means there is a transmission probability, so that's the peculiarity of the quantum mechanics. Clear? Okay, so now let's interpret this result, huh? So then I will stop. Okay. Okay, so if I take now, let's say if I take K tends to 0, what does that mean? So if you remember what is K, so our K square, that's equal to twice ME by extra square. Got it? If I take K tends to 0, okay, so it is a wave vector for what? So the scattering particles. Got it? That means my particles are slowly moving, okay, that are very slow enough. In that case, this T will be equal to 0. Is that true? So if I take now, okay, first case, if I take K tends to 0, R will go to -1 and T will go to 0. That means slow particles, which are slow enough particles, they will not transmit through the barrier, okay, but they will be reflected completely. This -1 means, okay, there is actually a phase change. So when something gets scattered, okay, reflected from some object, there will be actually simply phase change of pi. Clear? So E raised for I pi is -1. Got it? Okay, so now the other limit is, which is, okay, if I take now K tends to infinity, you will get R equal tends to 0 and T tends to 1. So that means if you are having high energy particles, they will transmit through the potential. Got it? Now these are not only the two limits. What is more important to this very problem is that there are actually the another values of Q, that this momentum Q, for which this you can make reflection 0. Okay, so that means for certain values of Q you can have this very potential, okay, and this potential step as a perfect transmission, okay, while there is a complete transmission. Clear? What are those values? Okay, so if I look at this formula for R, this I can make 0 for, okay, so R can become 0 if the sine of QA is equal to 0. Got it? I can make sine of QA equal to 0 so that this R becomes 0. So when it happens, so this T will become 1 always. Got it? So when sine of QA is equal to 0, this is equal to 1. Okay, for those values. Huh? Okay, so this will go to 0. So you will see twice IQ, that will cancel out. So got it? Okay, so what are those values? So it implies Q is equal to n pi. So it means I can, okay, so now what is Q? So I can write it as Q square equal to n square pi square by a square. I know Q square, that is twice m by extra square, okay, V naught plus k square, that's equal to n square pi square by a square, okay. So what you are having, so which implies V naught plus E, so I can have this thing as n square pi square, because k square is that extra square divided by twice ma square. It means I can control my potential, since V naught is the height of the potential, is it?
Yes,
E is the energy of the particle which gets scattered from this potential. Clear? So I can adjust my potential and energy in such a way, if it has these kind of values, these quantized values, I can make perfect transmission through this very potential. So I have a control over these very variables. Got it? If I adjust these values for a given problem in such a way that they take these values, there can be perfect transmission through that potential. Okay, so this is very experimentally feasible. So experimentally we are making transmission through barriers, just adjusting the values of this height of the potential and the energy of the particle. Got it? समझ आओ?